Lab 5, Modeling the Solar System. The purpose of this lab is to, through Newton's second law and the universal law of gravitation, create two models of the solar system, one factoring in interplanetary reactions and the other not, in order to calculate the length of a year on Earth. The result was that the model with interplanetary forces had a year of approximately 365.59 days in length, and the model without interplanetary forces had a year of about 365.70 days. This error of less than 0.04% between the two indicates that the Sun is the overwhelmingly significant reason for Earth's orbit. The length of a year is generally thought of to be 365.24 days, which differs from both of my calculations by less than 0.2%. Because of certain limiting factors, I made some assumptions in carrying out this lab. I treated each planet as a point particle since I was dealing with the length of orbit around the Sun and not the rotational aspect. In addition, I assumed that no forces other than the gravitational forces acted on the system. Also, since I only knew the average distances of the planets from the Sun and their respective average velocities, I assumed that these two values coincided at the same point in time, setting them as my initial condition. Also, because I did not have exact angles of velocity relative to the Sun, I had to set the velocities as tangential to the Sun. This made the planets' paths more circular rather than elliptical as they are in the real universe. Finally, I assumed that the orbits were in a 2D plane. One of the physics principles we are using is Newton's second law, which is F net is equal to mass times delta V over delta T. This can be rearranged to solve for final velocity, which can then be used to update the position of each planet. Also, Newton's universal law of gravitation will be used to calculate net force. We used this in the past, but instead of using data points to find the force of gravity, we're instead using this formula to predict the motions of objects. In my first model of the solar system, without interplanetary reactions, I created 9 objects representative of the 8 planets and the Sun, and placed them at their respective distances from the Sun in the positive y direction, with the Sun as the origin. I then inserted each object's mass and then entered their respective velocities in the positive x direction so as to be tangential to the Sun. I also created initial momentum vectors, for a reason I will explain later. I then defined my gravitational constant g and set my time step as 3600, the number of seconds in an hour. I then set a while loop and coded for Newton's second law and the law of universal gravitation for each planet, defining r as the displacement from the planet to the Sun and F net as the force of gravity between that planet and the Sun. I then set final momentum vectors and a print statement that displayed the time, position of the Earth, magnitude of the initial momentum, and magnitude of the final momentum. In order to determine the length of orbit of 365.70 days, I tested out times for my while loop and, looking at the print statement, found the one that got me closest to an x position of 0, since that is where the Earth started. Note that the position cannot be exactly 0 due to the finite size of my time step. The reason I included the final and initial momentum magnitudes of the Earth was to show that momentum is not conserved through the orbit, but rather increases. An object acted upon by a constant net force pointed towards the axis of rotation, otherwise known as the centripetal force, must have a constant momentum throughout to travel in a perfect circle, since there is not a component of dp dt parallel in that case. Since we can see that the momentum changed, we can see that the Earth's motion is slightly elliptical, despite our assumption about its initial velocity being tangent to the Sun. My second model was identical to the first, except that I included the forces of gravity from the other 7 planets on each planet, resulting in a total of 64 forces to account for. Also, F net was changed to the addition of all the forces on a particular planet. Although my prediction of the length of the year was fairly accurate, there were several factors that skewed the prediction. Because I was forced to make the earlier assumption about the average velocity and average distance from the Sun, I could not very accurately capture the true elliptical orbit of the Earth, even though I showed that the model was slightly elliptical. Also, my time step was too large to get my x position very close to 0 for my prediction, and lowering it would make the program crash due to the extremely long time of my while loop. Finally, the Earth in the real solar system has 3D movement, which I did not represent in this model. In order to examine the effects of the interplanetary forces by themselves, I decided to run my second model again, except with the Sun's mass as 0. As you can see, the planets travel in a straight line, demonstrating that the force of gravity from the Sun overshadows the interplanetary gravity forces and is virtually the sole reason for planetary orbit. Thanks for watching.